Guys, Shramee, and this talk is going to be about more on engineering slightly and like business slightly side of things. We're going to talk about some primitives and how you could um, think think a bit better in zk. Um, I'm Shramee. You can reach me on x.com/Shramee tweets. I optimize um, crypto math stuff like algos and stuff. I'm largest contributor on Consensus Gnark outside of their core team. I work on optimizing stuff like MSMs. Um, I did some optimization on SHA-512 for um, a library on Starknet, made it like 10x faster. In this talk, we will cover like some of the fundamental ideas and like building blocks that you can use to think about zk applications in a better way. And we will discuss some common zk designs and maybe look at some implementations. So let's get started. The first one, you probably are all used to this one. It's like commitments. So you commit to a chosen value and keep it hidden. It's just like a hashing thing. It's the stuff that we look for is that our committed value should remain hidden unless we want to reveal it. This is the hiding property. We also need the binding property, which means that if like once a value is committed, is it loud enough, guys? Yeah, sweet. It should be binding. So once you commit to a value, you should not be able to change it. We will talk a bit about hashing salts, which help to avoid like hash lookups. So if you take an action now, like hash it, and like that's part of your proof, public parameters, and then you or someone else tries to do the similar action later without salts, this will leak information about your action because it will basically disclose that this action has been done before. That's why you want to use like salts and stuff like that to keep it still hidden. A lot of people actually I've spoken to um, come up with ideas which actually don't really need any zk, and this could several stuff could be just done with a simple commit reveal. You commit to a hash. You commit to you have a pre-image of a hash, and later as more stuff happens, you could reveal it. For example, let's say you have a card game and I have my own deck, and um, someone has their own deck, and you want to have the game go, and you want to see at a point like who wins. So that kind of stuff can mostly happen without any zk with a simple commit reveal. Merkle trees are extension of like our hashing, hiding, and binding properties. They're basically like scaling your hashes. So we end up creating something like a binary tree of your hashes, and to prove that you've got something that is in the list, you just need like log n hashes. So say if you have like 124 items on the list, you just need like 10 plus 1 elements to prove that you have something that belongs on this list. Now we're getting into inclusion proofs. This is a very common type of proof, which is based on Merkle proofs. Merkle trees, and this powers a lot of stuff. For example, we will actually discuss about the practical stuff later. So this one basically means that you have like a public Merkle root, and you basically provide a path to one of the items on the Merkle tree, and that essentially proves that you've got this thing. And again, you just need here like the log n hashes in your proof circuit. So a bit about ZKPs, private and public inputs. Your public inputs are known to everyone. This is the you would want to use this on your public contracts to connect your ZK logic with your public logic. This would include commitments or shared state. And then we have like private inputs. These are secrets, but used when generating the proof. It's private information. So elaborating a bit more, whatever public inputs you use, the verifier will need to do a bunch of computation to integrate these public inputs into your proof verification. So a common practice here is to if you have multiple public inputs, you probably want to hash them together. So you just have like one single public input, and that is basically that basically reduces the number of like scalar multiplications and stuff that you need to do. Um, and you can just provide the whole pre-image of all your public inputs to the verifier. Verifier can hash them together, probably using some efficient hashing thing. And then it just needs to add one public input to your verification. And about private inputs, a prover can generate like any number of unique proofs for a given set of inputs. So what you might also want to do is maybe like hash the private inputs to have some sort of a nullifier, or your public inputs could represent your private input information, and um, a given set of private inputs would only work for a specific um, public input. So that is all. And any questions so far? Cool. That was rather straightforward. And um, now we can take a few routes. Like we can talk about how you would maybe use some ZK stuff to, let's say, prove how an agent can prove how you can prove that you got some response from an LLM or some LLM provider to make an action on chain for on chain agents. Or we could look into a ZK tiny game thing that I built quite a while ago. What would we prefer? Yeah. Yes. That's a very good idea. That's a known problem, and it exists, and there's no easy solution, fortunately, because
How about TE and a secure enclave?
yeah, you could do that, but that's not really ZK.
No, but a
Um,
secure enclave and ZK. Can you,
you could actually do an attestation and generate the ZK proof of an attestation,
yeah.
but the costs are largely prohibitive because you probably don't want to if you're building a game and you have like some NPC which is supposed to do your so also I do a lot of like autonomous worlds and ZK game stuff. So if you have an NPC that reacts in a different in a specific way
Yeah.
based on how what actions users are taking, so you probably don't want to have a TEE just for running an LLM inside there.
But you can have a hash somewhere, and of the particular software. There must be some way
Mm-hmm.
to do that.
No, no, no. You can do that. Actually, there are a lot of proof of concepts for this thing which are already working. Um, but the costs are prohibitive
Okay.
because I think like TEE is quite expensive. Yeah. Yeah, so we can either go through a game example that I built quite a while back, and I have like written circuits for it, so we can walk through the code and see how you would go about implementing something like that. Or we could talk about the AI agent thing, which I haven't done myself, but I have some inkling of how that might work. So let's do some voting here. For the ZK game thing, which has code, and we can walk through the code. We have 8 people here, and if we want to talk about AI agents, okay, we've got 3. We can try to wrap both up if possible, but we can try. But there's sorry.
Or is it without code?
What does that mean exactly?
You said there are two options, right? One is ZK
Oh,
game with code,
yes. The ZK thing that I wrote it a few months ago, probably in September or something, August probably.
but does the AI one have code?
No, I don't have any code for that, but I can describe how it might work.
Okay.
Yeah, not super. Yeah, like I haven't done it before, but maybe I can paint. We can actually probably, discuss and brainstorm on how it could be done. Yeah, sweet. So when you're doing an autonomous world or like a ZK, a game or an autonomous world where certain parts are ZK, we need to consider state transitioning. So we with our zk proofs we actually try to say that whatever change I'm making to the state is valid and follows the rules of the game. To make this happen, you need some sort of shared state for sure. And what you also need is commitment to uh, previous hidden state. So you can essentially form like a block, like a chain of proofs, so that you know that all the updates that are made on the state follow legal moves following a set of rules. And some commitments about the previous hidden state, yeah. So we're gonna walk through zk chase, which I was building. I was doing the zk stuff, and Balthazar, he's a dude who's very cool. Very cool. And he did the most of the contracts, the front end, and I did some of the zk stuff. Ba, 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 ba. Let's go through Noor because it's much more easier to, understand. Alrighty. Now, what am I doing here? Yes, sir. I don't really want this. Can I just delete this thing here? Yeah, I think that's better. Maybe delete this one as well. Ah, perfect. Sorry? Oh, that's a good idea. But I don't remember which project that is, so it's gonna take a long time probably to find it. Let's see if we can. Ah, good. Thank you. Yep, let's do that. Here's my GitHub. CK Chase Shift A. Aha, there we go. So this got a bunch of stuff. You can have a look later. Let's just walk through node.com, no R stuff. And yeah, here we go. So there should be a main function here. I'll get at that. Command Shift plus. Is that visible enough? If you guys want, you can also come a bit forward, but uh, if you want to read. But if it's readable, then we can just go forward. So let me describe the game a bit. So you have like a tile map. You move from one coordinate to the other. The rule is that the coordinate that you move to has to be in one of the east, west, north, or south direction. Like you cannot do multiple tiles per move, and there is like like some area on the map which is like the forest, and when you're in the forest, like the game is public by default, but as soon as you step in the forest you start using zk to still to make your moves. um yeah, so your location is not revealed. Yeah, so let's just walk through this. The objective is the game is very simple and rather stupid. I wanted to do something like battle brawlers, which you might have some inkling of how it works. Basically, you are just like shooting people, and you hide in the bushes, you strategize, move around. It's a game like that. But for this one, we're just like trying to find some coins and trying to avoid getting killed. When a player moves into you, you get killed. So we pass in a map, which is basically like a bitmap of all the places that users can hide in. So you can only hide when that coordinate is position 1. And then we have like a previous position hash. This is what actually forms the chain of proofs to make the state transitions, held by the rules. You cannot jump around. Then we have previous position. This is a private position. And this is just used to match with the previous position hash and do the apply the move to the position. We have some salt, which is used for hashing, and it returns new position hash for saving on chain. So the map is currently like 256 bits. So we have like two 128-bit numbers to represent the map. And here we just assert first that the previous position with the salt gives us the previous position hash, so that we link to the previous proof. Then we make move. Make move is essentially going to take like previous position and apply the move to it, and then we get the new position. We try to make sure that the new position that the player is moving into is a bush, which we check with the map representation here, and we check if if the bit at position x and y is a 1 bit, because that's the only that's only the place when we want to allow people to have a zk position. And we just assert that it's a bush. Then we compress the position back, hash it, and increment the salt. And this hash is then stored on chain, which can later be connected with um, previous proof to make sure that it's going step by step. Let's go through tests to see like how it works in action. We have a global map here, and we have this map represented as an array. This is like the bitmap. So you can see like there's a zk area here on the map and zk area here on the map. And we're going to spawn some treasure chest on the 0 places which are not hidden. And players try to just move around, and they try to stab each other, sort of like chase each other. And yeah, so here we're gonna see in this test, we basically check that it correctly recognizes the bush, and our this function over here, map bit function, works correctly. And we do it for a bunch of random positions. And finally, this is like the whole like a full test, in which we provide the salt, the previous position hash, the move that we want to make, 0, 1, 2, 3, or it's like probably like up, down, left, right, something like that. Yeah, up, down, left, right. So we're probably trying to move down here, and then we just assert that the result hash is what we expect. So that was pretty much it, and you're welcome to look at the repo if you wanna. So now we can probably do the other. Anybody got any questions about this? Yes.
Yeah. The yeah. For the treasure chest part, I didn't see the code.
So the treasure chest is not spawned by the ZK circuit. It's spawned by the contract.
And where was the zk code in
Sorry?
the zk code, the zk circuits code?
That is in ZK circuits. Don't go to Circom. I was writing Circom and I got pissed off that I cannot do modulo, so I decided to use NOR instead. It's halfway done, but anyway, ignoring that. Here it's in zkChase, ZK circuits, NOR.
Okay, thanks.
The fact that it says why, does that mean you have proven? Does that mean this code is been proven, or what does that mean?
That just means that we are using NOR to write this. Like, it's just an arbitrary DSL that you could use. It's very convenient.
Is it convenient or high quality? Which one?
Both. It's like Rust, so it's very type safe. You don't make mistakes, and it's got a very nice testing framework baked in. It's got support for integers, pretty much anything you could ask for, everything you want to
Would
ask
you
for.
generally recommend it over what?
Circom. Circom is shit. It's not shit. Like it's old. Testing is so annoying because you can't write tests easily, and it's hard to understand. It's a lot more math. You cannot have like well-defined structures as you might wanna in a good like evolved system like a game. So maybe I have something like well-structured here, but maybe not. No, nothing particularly well structured here. It was quickly put together. But it's just convenient. It's just far more readable. Yeah,
How popular is it?
it is quite popular. It's from Aztec, and it pairs very well with Berettenberg, which is their backend for generating proofs. And one tiny thing is that it's slightly slow to prove on the client side compared to Circom, which is why I might actually, so personally, when writing something that is more performance, I have to be a bit more aggressive on the performance. I would write it in Gnark, which is like, maybe I was showing before, I contribute a lot to it, mostly optimizations. With Gnark, you can generate R1CS, which you can do front-end proving much faster than NOR. But if you're building more complicated systems, it's more convenient to use NOR.
Thank you.
Sure. Any other questions, guys? Cool. So I guess we've got. Do we have any time left?
We do.
Nice. So we've got some time left, and we can talk about trying to have your ZK agent. We can try it. Like your agent does something on chain, and you basically want to prove that the agent is acting based on some response that it received from a specific entity, say OpenAI. So the way I see this working could be with like a zKTLS sort of a setup. Let me see. Maybe I can just pull the whiteboard or something like that.
have a marker.
Oh, thank you very much. So, high level, with zKTLS, you can sort of prove that you got a response from some specific entity. Let's just take OpenAI because it's going to make our discussion simpler. So let's say your agent does like API calls to OpenAI and it receives a response. And with zKTLS, what you can do is basically generate whole internet, the whole HTTPS thing actually uses this thing called like TLS, which is, I don't know, some transportation layer or something. I don't remember it all a long time ago. So what you can do is you can prove that you got a response from a specific entity. But now there are two gotchas here. So first, you need to trust someone to tell you what an OpenAI certificate looks like. And you need a proxy to sort of prove. Okay, well we can talk about it low level. So with TLS, what happens is that you are like a user or something like that. Yeah, and this is the server, which is OpenAI. Let's put the user here. Let's say bot, because our user is the bot. So what will happen right in the beginning is like these guys will do sort of like a handshake. These things probably look like a hand or not, but they do this handshake thing where they share like a common key. And then what happens is that all further communication happens via this key. So the challenge here is that while you can show with the CK proof that you got this key from this entity, but um, you cannot prove that what you are decrypting is a response that you specifically received from them. So let's say you have this sort of setup here where you can say that I got this key, and here is the response that I received, let's say, which is some sort of arbitrary JSON. And you say that I've got a key which decrypts this encoded message into something that you can understand, some JSON stuff. So that is actually not enough to basically prove that this is from OpenAI, because though you have a valid key, you cannot prove that the response that you received is actually from OpenAI and not some arbitrary JSON that you put yourself together. So what we need for this to happen is we need to have like some party in the middle that is gonna watch your traffic. It's gonna say, oh, bot said this, OpenAI said this, then bot said this, then OpenAI said this. It doesn't know what's actually being talked about, but what it does know is like who is sending message, the direction of the message. So now what happens is you've got this middleman, sort of, like not a middleman, because he can't really see what you guys are talking about, but he can attest that this encrypted message is from this party, this encrypted message is from this party. And then finally you can say that, oh, see, I have a key here which will decrypt this specific encrypted message. And I'm going to make use of this to make some transaction on chain. So that's how, so the person in the middle, the proxy, is going to say, yes, the message, that the encrypted message that this guy claims to have a key for did indeed originate from OpenAI. So via me, you can prove that you have a valid response from OpenAI. The middle person could be like a simple proxy, which people maybe trust. It could be some sort of a distributed proxy with some sort of like MPC or stuff like that. Or it could be a TE. So any questions?
The middleman would know not only where it came from,
Mm-hmm.
but it would also know the size of the message, of course, right?
It will know the message itself, but encrypted.
Right. So therefore, it knows the size of the message.
Um, Depends. I haven't really looked at what the responses look like, but it depends on encryption, I guess. If the what encryption algorithm gives you is like proportional to the size of the message, then he gets
But the concern I have is in the model that you gave,
yeah.
there's a potential man-in-the-middle attack that what comes in is different from what goes out. How do you protect against that?
Sorry, can you repeat that?
So,
Yeah.
so the concern is something comes in from OpenAI,
Mm-hmm.
and then the next thing that happens,
Yeah.
the middleman sends a different thing out. How do you discover that?
Yeah, that's a very good question, and this has been solved for ages. The whole purpose behind TLS is to solve this exact problem.
Right.
The middle person cannot change the message because the message is encrypted by the shared key between
Oh, that's right.
the
Yeah, you're
bot
right.
and
You're right.
OpenAI.
Okay. Good point. Good point.
Yes.
Got it. Got it.
Any other questions? Yes.
How is the key shared? Is it also through a proxy or?
Dude, actually, that's a very good question, and I'm like so upset that they're not using something like Diffie-Hellman key exchange or something, and that would make this protocol like so much easier to implement. If they use like Diffie-Hellman key exchange, you have your bot has its own private key, OpenAI has its own private key, and they use like elliptic curve based signing. So you take this dude's public key, multiply it by your private key. This dude takes your public key, multiplies it by their private key. And the way private keys are in elliptic curves is like let's say your private key, bot's private key is B, the lowercase b, and then you multiply it by this curve generator, and that is your public key. So for OpenAI, they're gonna have like O, and their public key is gonna be O.G. O is the private key of OpenAI. And now what you do in Diffie-Hellman key exchange is this guy is gonna take this dude's, OpenAI is gonna take your bot's public key, BG, and it's going to multiply it by its own private key. It knows its private key, right? So it's going to do b.g.o. And what bot is going to do, bot's going to take OpenAI's public key, which is o.g, and then it multiplies it by its own private key. So now you see, like, OGB or BGO is the same thing. So this could have been used, and it would make like zKTLS like a dream come true. Because now you don't need a proxy, now you don't need anything. But unfortunately, this is not the case. The handshake is basically you share what you want to use, sort of. And it's like probably randomly generated and does not hold any deterministic features, sadly.
So can you explain why that's not being used?
Sorry?
Why is that not the solution? Why is OpenAI not,
I think it's a matter of adoption, because TLS has been around for ages. People didn't quite think what they might want to do. Another challenge with this is that the browser needs to keep a private key, which inherently like was never safe, because people can sneak into your browser stuff. There's malwares and stuff. So I think what they did is that they designed this simple thing which would work for them and for users.
but in principle, with bots now being able to live on the blockchain,
Yeah.
and certainly even being able to maintain private keys in a TEE. I don't see is there any theoretical reason why the simple Diffie-Hellman approach wouldn't work prospectively.
It would work. The thing is, the whole point of zKTLS is its generality, because you can apply it to pretty much everything,
Good.
because everything is using HTTPS, everything is using TLS, and you just have this unique construct which allows you to basically operate with any of the services. With this specific construct, you would require people to implement this, both on the API side as well as the bot side. Bot side, you're controlling it, very straightforward to do, but someone will need to make an appeal to OpenAI or...
But why can't we do it with DeepSeek?
Yes, you could do that. Actually, I just had a bingo. I was just pointing that because someone could actually do
We do
an LLM which
DeepSeek
actually...
LLM, and on the bot we can do it anyway.
Yeah.
So now we have an infrastructure that
Yes.
can instantly work with standard protocols, standard Diffie-Hellman.
Yeah. Actually, it's very straightforward to do, and someone could probably do it for sure.
What would it take?
Nothing. Weekend.
Let's do it.
Yeah. Cool. So, any other questions, guys?
There are certain protocols like Reclaim protocol, for example.
Sorry, what protocol?
Reclaim protocol.
Okay,
which
so
uses ZK.
my brother tells me that used to tell me that I lived under a rock in Singapore because I had no awareness of what's happening. So I don't know about that protocol.
Okay.
What does it do?
But my general question is, does it matter how decentralized a protocol is in terms of how your data is being stored? If, let's say, I'm using an application and I'm sharing my data through Reclaim protocol,
Yeah.
how much of importance is decentralization here? And are you aware of any decentralized protocols that I can use ZK with?
I am not sure if fully comprehend the question, but if it is with respect to, the zKTLS thing, the proxy, if it is decentralized, it's definitely better, because then you have more people which in the pool, and one person might fuck you up, but like 100 people might not fuck you altogether. So
Yeah.
that way decentralization does help. But can you explain your question a bit more?
My question is, if I'm using such technology,
Mhm.
I'm relying on a third party to
Mhm.
verify my information, and I'm sharing my information through that protocol.
Mhm.
What I'm trying to understand is, how secure is it? Yes, we're using ZK and it's not being shared with the application or the servers, but the third party that is verifying that I am an original user,
Mhm.
how trusted is that third party, or how far are we from having a protocol?
Okay, so are you proving your, I don't know, like that you are a specific user with something like OAuth, or how are you proving?
Yes, I'm verifying that I have an X account of over 1,000 followers,
Right.
and I'm verifying that I shared the transaction
Uh-huh.
to you through my bank account without sharing my bank statements. So there needs to
Okay.
be a verifier here using ZK.
Blockchain, like you can so the apps built on like Aztec is like you can do private transaction, like if this is the answer to your question, is like it's like public trust decentralized plus the transactions are being like private over there. The dApps built on Aztec is like, yeah, they they provide these kinds of stuff if you're concerned about that.
I think we need to talk about this after this
Yeah,
more in
sure.
detail,
Yeah, let's
just to
do.
check out the technology. Thank you.
Cool. So anybody else? Cool. So looks like we're good here. Yeah. Cool.